In this video, I discussed the big O notation. The origin of this notation is in the 1894 book of Paul Bachmann, where he is estimating the total number of divisors, tau of n, of all numbers up to and including n. Bachman uses the floor function of Gauss. He cleverly exploits the double counting method to do this. This leads him to a paper of Euler, in which Euler estimated the sum of a harmonic series. We will get to see the master craft of Euler in the process. Euler proves that the finite sum of a harmonic series is of the size of logarithm of n. As a result, tau of n is of size n times log of n. I discussed the very beautiful proof of this, and one cannot but marvel at the skill and simplicity of one of the greatest mathematicians of all times. The big O notation of Edmond Landau is formally introduced, and important applications in computer science are discussed. You will learn to estimate the time complexity of the important constructs such as a simple for, loop, if then else, nested loops and function procedures. A recurring theme in this video is the principle of double counting. I give 3 applications of this. Finally, I give a visual proof of the sum of a geometric series and derive the logarithmic series which Euler used in showing that the partial sum of a harmonic series is of order big O of log n. There are 2 important problems given as exercises. Big O notation. Big O notation, with a capital letter O, not a zero, also called Landau's symbol, is a symbolism used in complexity theory, computer science, and mathematics to describe the asymptotic behavior of functions. Basically, it tells you how fast a function grows or declines. Landau's symbol comes from the name of the German number theoretician, Edmond Landau, who invented the notation. The letter O is used because the rate of growth of a function is also called its order. For example, when analyzing some algorithm, one might find that the time, or the number of steps, it takes to complete a problem of size n is given by t n equals 4n squared minus 2n plus 2. If we ignore constants, which makes sense because those depend on the particular hardware the program is run on, and slower growing terms, we could say t n grows at the order of n square and right. T n equals capital O, parenthesis n square. Origins of concept of orders of growth. German mathematician Paul Bachmann is credited with introducing the notation to describe orders of magnitude in his 1894 book, Die analytische Zahlentheorie, Analytic Number Theory. His overall goal was to present a full treatment of analytic number theory, which he conceived of as investigations in the field of higher arithmetic which are based on analytical methods. In Chapter 13, Bachman turned his attention to the analysis of number-theoretic functions, which included a basic theory for the number of divisors and sum of divisors functions. Of interest to us is the fact that Bachman introduced the big O notation at this point, in order to give a precise statement for the growth of the number of divisors function, which he denoted by t. In the table displayed on the slide, the number of divisors t, k, is shown in the third column. For example, the number 6 has divisors 1, 2, 3, and 6, and so, naturally the number of divisors of 6 is 4, and sum of its divisors is equal to 1 plus 2 plus 3 plus 6 is equal to 12. The number of divisors of k is obtained by counting the divisors in the row corresponding to k. Bachman did not want to estimate the growth of t, n, but rather its summation function tau, n, which gives the count of all the divisors of the numbers from 1 to n. Thus, tau, n, can be calculated by counting all the divisors in the rows k equals 1 to k equals n. For example, tau, 9, is obtained by counting all the numbers in the shaded red triangle. In mathematics, many important results are a consequence of a simple fact. If we can count in two different ways, then a nice identity appears. So, to calculate tau, 9, we can first count the divisors in each row, and then add the counts. In other words, we are adding up all the entries in the t column which are not above t, 9. Another way to count the elements is as follows. Count the divisors in each column and add the totals. We must get the same result, in this case tau, 9, which is 23. Now, what does the count of a column represent? Let us look at the first column. It consists of all ones. This is because 1 divides every number k. So, count in column 1 represents all numbers which are divisible by 1. Hence, the number of entries in first column is 9, which is what you see in the last row. How about the second column? It consists of all 2's. So, the count of elements in column 2 represents all numbers which are divisible by 2. In the example shown, this count is 4. Does this make sense? Well, indeed. There are 4 numbers, namely 2, 4, 6, 8, which are divisible by 2, or equivalently, which are multiples of 2. Observe that 4 is the quotient obtained when 9 is divided by 2. This is also called the integer part, or the floor of 9 by 2. Let us do one more column, say, the fifth. It consists of all 5's. So, the count in column 5 represents all numbers which are divisible by 5. In the case at hand, there is only one number divisible by 5. Once again, note that the integral part of 9/5 is 1. Spend some time focusing on the next slide, where you should work out the case n equals 6. Let me summarize Bachmann's result. Tau, n, the number of all divisors of natural numbers up to n, which is nothing but the sum t1 and t2 up to tn, is equal to the sum of the integral part of n divided by k as k runs from 1 up to n. While this is a convenient alternative formula for tau of n, Bachman wanted an analytic estimate of its magnitude. Given n, roughly how large is tau of n? The problem is the integer part function is discontinuous, so applying methods of calculus is cumbersome. He replaced the floor function by a continuous part and a discontinuous part, which was simple to estimate as it was always between 0 and 1. This formula provided the starting point for his argument, which can be seen on page 401 of his book. Every rational number x can be split into its integer part and a fractional part. For example, the number 9/2 can be expressed as 9 divided by 2 is equal to 4 plus 1/2 equals integer part plus fractional part. The number 9 out of 5 can be expressed as 9 divided by 5 is equal to 1 plus 4/5. Therefore, we see that the integer part of a number x can be written as x minus its fractional part. Note that the fractional part always lies between 0 and 1, irrespective of the number. Bachman used the Greek letter rho to denote the fractional part. Since each of the n terms in the sum tau of n gives rise to its own rho, and each rho lies between 0 and 1, we know that tau of n differs from the sum k equals 1 up to n of n divided by k by less than n. As a result, we obtain a nice formula for tau of n, as shown in the slide, and where r is the sum of the rows and is less than n. Enter Euler. Euler, 1707 to 1783, was born in Basel, and entered the University of Basel at age 13 to study theology. He also had private tutorials in mathematics from Johann Bernoulli, 1667 to 1748, who was professor of mathematics at the University of Basel. Johann recognized Euler's mathematical gift and convinced his family to let him switch to mathematics. Euler was excellent at computation and had an essentially photographic memory. He had great persistence and returned over and over again to problems that challenged him. Euler spent much effort evaluating the sums of reciprocal powers, as shown on the screen, for integer m greater than or equal to 2. These series go by the name zeta. He obtained the formula zeta of 2 equal to the square of pi divided by 6, solving the Basel problem, as well as formulas for all even zeta values. He repeatedly tried to find analogous formulas for the odd zeta values zeta, 2 and plus 1, which would explain the nature of these numbers. Here he did not completely succeed, and the nature of the odd zeta values remains unresolved to this day. Let us introduce some notation for the partial sum of zeta function as shown. Observe that the middle series, Hn, 1, was precisely what Bachman was trying to estimate. In a paper written in 1731, on harmonic progressions, Euler summed the harmonic series in terms of zeta values as follows, and he computed Euler's constant to 5 decimal places. This result essentially tells us that the harmonic series is of the order of logarithm of n. He proves his result by using the expansion of the function logarithm of 1 plus x, which was found by Nicolas Mercator, circa 1620 to 1687, in 1668. I shall explain his proof, because it is an excellent example of computing things in two different ways. Here you can see a master mathematician at work and is truly inspiring. On the screen you can see 5 rows obtained by successively substituting 1, 1/2, 1/3, 1/4 and 1/5 in the series for the logarithm. Observe the terms on the right side are nicely aligned. The first column consists of the reciprocals of natural numbers, i.e., the terms of the harmonic series. The second column, save for the factor -1/2, are the squares. The third column apart from the factor 1/3 are the cubes, and so on. Now here is Euler's magic. He sums the first n rows. On the one hand, the leftmost column telescopes, and we are left with the logarithm of n plus 1. From the right-hand side, the first column gives exactly what Bachman wants, namely, the sum of n terms of the harmonic series. The second column onwards are just the multiples of the partial sums corresponding to the zeta function with argument 2, 3, 4, etc. Back to Bachman. Using Euler's result in the earlier formula for tau of n, we arrive at Bachman's original conclusion, that the summation function satisfies the relation tau of n equals n times logarithm of n plus big O of n. Alongside his final result, Bachman explained that the big O of n notation referred to a quantity whose order did not exceed the order of n. Unfortunately, he did not clarify this definition, even though the concept was in use throughout the remainder of the book. 15 years later, Edmond Landau gave a precise definition of the big O notation. Formal definition. For the formal definition, suppose f and g are two functions defined on some subset of the real numbers. We write f of x is equal to big O of g for x tending to infinity if and only if there exist constants n and c such that mod of f of x is less than or equal to c times mod of g of x for all x bigger than n. Intuitively, this means that f does not grow faster than g. In computer science, typically only positive functions with a natural number n as argument are considered. The absolute values can then be ignored. On the slide is a table of classes of functions that are commonly encountered when analyzing algorithms. The slower-growing functions are listed first. C is some arbitrary constant. The above list is useful because of the following fact: if a function f is a sum of a fixed number of functions, one of which grows faster than the others, then the faster-growing one determines the order of f. For example, the order of growth of the function 10 times logarithm of n, plus 7 times logarithm of n cubed, plus 6 times n squared, plus 5 times n cubed is big O of n cubed. One caveat here: the number of summands has to be constant and may not depend on n. Note that when we write T, n, is equal to big O of n, we are abusing the equality symbol, since it violates the axiom of equality: things equal to the same thing are equal to each other. 4. Both the functions 4 times n and 11 times n are big O of n, but they are not equal. Because of this lack of precision, some mathematicians and computer scientists prefer to define big O of g as a set-valued function, whose value is all functions that do not grow faster than g, and use set membership notation to indicate that a specific function is a member of the set thus defined. Applications to analysis of algorithms. Efficiency of an algorithm depends on several factors. CPU time, memory, disk usage, network usage. In analyzing an algorithm, we mostly discuss time complexity, CPU usage, and space complexity, memory usage. Be careful to differentiate between performance, how much time/memory/disk is actually used when a program is run. This depends on the machine, compiler, etc., as well as the code. Complexity, how do the resource requirements of a program or algorithm scale, that is, what happens as the size of the problem being solved gets larger? Complexity affects performance, but not the other way around. For example, a very efficient algorithm can be ruined by a poor code. Time complexity. The time required by a function/procedure is proportional to the number of basic operations that it performs. Here are some examples of basic operations. 1 arithmetic operation, example, addition, multiplication. 1 assignment, example, setting a variable to 0. 1 test, example, testing if x is equal to 0. 1 read, of a primitive type, integer, float, character, boolean. 1 write, of a primitive type, integer, float, character, boolean. Some functions/procedures perform the same number of operations every time they are called. For example, stack size in the stack implementation always returns the number of elements currently in the stack or states that the stack is empty. Then we say that stack size takes constant time. Other functions/procedures may perform different numbers of operations, depending on the value of a parameter. For example, in the bubble sort algorithm, the number of elements in the array determines the number of operations performed by the algorithm. This parameter, number of elements, is called the problem size/input size. When we are trying to find the complexity of the function/procedure/algorithm/program, we are not interested in the exact number of operations that are being performed. Instead, we are interested in the relation of the number of operations to the problem size. Typically, we are usually interested in the worst case. What is the maximum number of operations that might be performed for a given problem size? For example, inserting an element into an array, we have to move the current element and all of the elements that come after it one place to the right in the array. In the worst case, inserting at the beginning of the array, all of the elements in the array must be moved. Therefore, in the worst case, the time for insertion is proportional to the number of elements in the array, and we say that the worst case time for the insertion operation is linear in the number of elements in the array. For a linear time algorithm, if the problem size doubles, the number of operations also doubles. For a quadratic time algorithm, if the problem size doubles, the number of operations will quadruple. How to determine time complexities? In general, how can you determine the running time of a piece of code? The answer is that it depends on what kinds of statements are used. Let us suppose that a program code segment has a sequence of k statements. Statement 1. Statement 2 up to. Statement k. The total time is found by adding the times for all statements. Total time equals time, for statement 1, plus time, for statement 2, plus plus time, for statement k. If each statement is simple, only involves basic operations, then the time for each statement is constant and the total time is also constant. They go of 1. If then else. Most computer languages provide a if-then-else construct. If condition is true, then execute block 1. else execute block 2. And if. Here, either block 1 will execute, or block 2 will execute. Therefore, the worst case time is the slower of the two possibilities. Maximum of the two times. Time to execute block 1 and time to execute block 2. If block 1 takes big O of 1 and block 2 takes big O of n, the if-then-else statement would be big O of n. Loops. For I equals 1 up to n minus 1, execute sequence of statements, end loop. The loop executes n times, so the sequence of statements also executes n times. If we assume the statements are big O of 1, the total time to execute the loop is n times big O of 1, which is big O of n overall. Nested loops. For I equal to 0 up to n minus 1, execute outer loop. For j equal to 0 up to m minus 1, execute inner loop, end inner loop, end outer loop. The outer loop executes n times. Every time the outer loop executes, the inner loop executes m times. As a result, the statements in the inner loop execute a total of n multiplied by m times. Thus, the complexity is big O of n times m. In a common special case where the stopping condition of the inner loop is j less than n instead of j less than m, i.e., the inner loop also executes n times, the total complexity for the two loops is O of n squared. Statements with function/procedure calls. When a statement involves a function/procedure call, the complexity of the statement includes the complexity of the function/procedure. Assume that you know that function/procedure f takes constant time, and that function/procedure g takes time proportional to linear in the value of its parameter k. Then the statements below have the time complexities indicated. F, k, is big O of 1. G, k, is big O of k. When a loop is involved, the same rule applies. For example, for j equal to 0 up to n minus 1 loop, G, j, end loop, has complexity n squared. Big O of 1 plus big O of 2 plus plus big O of n, which is big O of n squared. Observe that here, the number of terms being added is not fixed. It is varying with n. So we have to heed the caveat mentioned earlier while computing the complexity. Before I close, let me show you 3 interesting applications of the principle of double counting. The first one is a cute one which can even be taught to children in primary classes. Shown is a picture of 24 playing cards arranged in 4 rows and 6 columns. Each row has 6 cards and each column has 4. If we count by rows, then the total number of cards is 4 times 6. On the other hand, counting by columns, yields 6 times 4. So 4 times 6 equals 6 times 4. This is the commutative law for multiplication of natural numbers. The second example is from college trigonometry. One of the many gems which Euler gave us is the famous CIS formula. This expresses the trigonometric functions sine and cosine in terms of a complex exponential as displayed. Euler considers the series representation of the exponential function. He is a brave mathematician and replaces the real number x by a complex number I times theta. Here I is the imaginary complex number square root of -1. He then observes that the even powers of theta sum to cosine theta and the odd powers sum to I times sine of theta. Euler substitutes theta by n times theta and once more boldly uses the multiplicative property of the exponential function. Finally, he uses the CIS again and then using the binomial theorem expands the right side. He equates the real and imaginary parts on both sides of the resulting identity. The result is an expression for cosine of n times theta as a polynomial in cosine theta. It is indeed wonderful to see the deft hand of the master mathematician Euler, who skillfully uses the magic of double counting repeatedly. The final example is from Euler's original paper where he obtains a remarkable identity connecting the zeta functions. The proof is again using different ways of adding and is similar to the harmonic series method. Finally, just for completeness, I give a visual proof of the sum of a geometric series. Let me consider a rectangle with sides A and B. Suppose R is any number between 0 and 1. Divide A and B into two parts each as shown. The ratio of the lengths of the two pieces is R divided by 1 minus R. This subdivision gives us two rectangles colored red and green and a remaining piece which is of skin color and whose sides are R times A and R times B. I shall call the red rectangle the vertical piece and denote it by V. The green rectangle the horizontal piece and denote it by H, and the skin-colored piece I denote it by R. Observe that area of V is 1 minus R times A, area of H is 1 minus R times A, and the area of R is R squared times A. So, we have a nice interpretation of R. It is the ratio H over V. Moreover, the square of R is the ratio of area of R divided by A. The area A can now be written as A equals V plus H plus R. The sum of V and H is 1 minus R times A plus AR. Since I am going to iterate this process, let me summarize in words the process. If I take any rectangle with sides A and B and split each side into two parts and the ratio R over 1 minus R, then the original rectangle splits into three rectangles V, H, and R such that the area of the original rectangle is 1 minus R times A plus AR plus a remainder whose area is A times R squared. The next three slides show three steps of this iterative process. Remember, at the beginning of a new iteration, the R of previous iteration is the new area. After n steps, the remainder area is A times R squared to the power n. This tends to 0 as n approaches infinity. If we let B equals 1, then we have the sum of an infinite geometric series. In this series, replace x by minus x and integrate once term by term to obtain the series for the logarithm of 1 plus x. Summary. Let me summarize the contents of this video. I began this video with a brief history of the origin of the big O notation. A problem in number theory, on estimating the number of divisors of all numbers up to and including n, led Bachman in expressing tau in terms of the floor function of Gauss. He cleverly exploited the double counting method to do this. This then led into a paper of Euler, in which he estimates the sum of a harmonic series. We get to see the master craft of Euler in the process. The finite sum of a harmonic series is of the size of logarithm of n. As a result, tau of n is of size n times log of n. I then gave a formal definition of the big O notation of Edmond Landau. As applications, we saw that the stack size operation is constant in time and inserting an element in an array is linear in the size of the array. I showed you how to estimate the time complexity of the important constructs such as a simple for, loop, if then else, nested loops and function procedures. A recurring theme in this video is the principle of double counting. I gave 3 applications of this. Finally, I gave a visual proof of the sum of a geometric series and derived the logarithmic series which Euler used in showing that the partial sum of a harmonic series is of order big O of log n. I will leave you with a few important problems to estimate their time complexity. Have fun!